So just like before, every user and the server can interact with each other. However, unlike before, every user can send a message to any other user. So if user I want to send message to user J, I don't care how he got connected to it, he can do it. And to model the fact that everything went through the server and they were using PKI in the star model, here we're allowing the server to know the origin and destination of the message, but he doesn't know the content. And finally, we're going to give the server the additional power that he can actually block messages. So if a user want to send a message to another user, in the star model, it had to come through the server, so we can just not send it. So here we're giving him the ability to just simply block the message. Right. So this is our model. Now I'm going to show you our results. Our first result is actually a committee election protocol. So this is a variant of Fege's original committee election protocol, which was for the standard model where there was a broadcast channel and everyone was polynomial. So we give a variant of that protocol for the gMPC model. Essentially, at the end of the protocol, all parties will agree on a small committee, say log square of the number of users, such that this committee, the fraction of malicious users in this committee is not going to be much higher than the original number of malicious parties that there were in the protocol. So although the original protocol was extremely elegant, in the gMPC model, it's actually going to be, there are going to be a lot of complications, as I'm going to show you on the next few slides. But before that, we have a second result, which uses this committee election protocol, and we actually provide a general protocol. We show that for any functionality with whose output length is not that much higher than the number of users, we show that there exists a secure protocol computing it. And security holds assuming only a constant fraction of the users can be corrupted, where this constant is strictly less than 1/8. And our construction also assumes a fully homomorphic encryption. However, interestingly, if the function can be computed using a sufficiently small and shallow circuit, then actually we can compute it without FHE, and we only need symmetric cryptography to do this. And this is important because small and shallow circuits also include important functions such as sorting and aggregation, both of which have important applications to the shuffle model of differential privacy. And finally, like I mentioned before, we can show that any secure protocol in this model can be transformed into a secure protocol in the star model, assuming PKI. And interestingly, we also show that with assuming PKI, we can increase the constant alpha that we can tolerate. So now we can tolerate strictly less than 1/4 rather than 1/8. Very roughly speaking, this is because without PKI, the server can still remove some of the users and replace them with malicious ones. And in our protocol, is sort of double the number of malicious users that he can work with. Okay, so now I want to show you our techniques, but to give you the full protocols will take me a few hours. So instead, I will just tell you why it will take me a few hours. So there are a lot of challenges in the gMPC model. I'm going to show you 4 of them. The 4 main challenges. So the first one is distinguishing between a server blocking a message and the malicious user simply not sending the message. So we need to handle that issue. There's a second challenge of DDoS attacks, because I'm reminding you the adversary is still polynomial. So even though even if he doesn't corrupt the server and only corrupts the users, he can still flood the network with garbage messages. Our third challenge is about concurrent compositions. There are going to be a lot of protocols running concurrently. So we need to argue that they're still secure even when they're composed in such a way. So you might say, okay, just use UC, but UC requires CRS, which we don't assume. And there are also other security notions such as bounded concurrent composition, which probably requires the users to be polynomial time, which again, we don't assume that. And finally, there's the challenge of how to verify very long statements. So because the server is significantly more powerful than the users, he's going to do all the heavy lifting of the protocol. So he has to do the computation of the function, and that means the users have to verify that the server did it correctly. However, notice that the users are only polylogarithmic, while the computation can be polynomial. So this means that the statement itself is too long for each user to read on its own. So we'll have to somehow view all users as one single verifier and somehow allow them to verify the entire computation together. Okay, so these are our 4 main challenges, and for the remaining time I have, I will talk about the first one, how to distinguish blocks from bots. So pictorially, this is the image. So on the top, we have a malicious user not sending a message, and on the bottom, we have the malicious server blocking the message. So notice that the receiver cannot distinguish the 2 scenarios. But actually, there is a sub-challenge to this. Let's say that somehow it does distinguish the 2 scenarios, and he knows that is in the bottom the scenario. He knows that the server is malicious. So now he wants to tell it to everyone else. So he wants to shout to the world, hey, the server is malicious, we need to abort the protocol. But notice that he cannot simply just send messages to everyone because the server can just isolate him, it can just block all messages. So even if we somehow know that the server is malicious, we still need to figure a way to allow the users to tell it to everyone else. So to solve both of these challenges, we introduced 2 tools. The first tool is the tool of personal committee, which, unlike Fager's committee election protocol, where everyone agree on a single committee, here there's going to be, for every user, a single committee, which the server and the user sample together using a coin tossing protocol. So they're going to sample together a personal committee for the user, which is, again, relatively small. And what we're going to do with this personal committee is that now, when the parties want to execute some protocol, instead of the users talking to each other and to the server, we're going to replace the users with their personal committees. So they're going to run some MPC protocol inside. There are a lot of subtleties because they're still blocking within those committees, but essentially they're going to run an MPC protocol to simulate a single user. So why does this work? So let's first consider the case where the server is honest. So notice that if the server is honest, then that means that even for malicious users, all personal committees are chosen uniformly at random, which means that the fraction of malicious users does not increase by too much. So this means that almost all of the users in each personal committee are going to be honest, and therefore these are effectively honest parties. And additionally, notice that because the server is honest, it means that no message is going to be blocked. So what this means is that if the server is honest, then every message that is sent will be received. So what does this tell us about the case where the server is malicious? Well, it means that first, if he blocks the message, then it means we caught him. It means that he cheated. And second, even if the personal committee of the sender corresponds to a malicious user, then it means that potentially all users inside that personal committee are corrupted, and they can withhold the message. But again, just like before, this would never have happened if the server was honest. So again, we actually caught him in this case. So this solves the first problem, how to distinguish between the case where the server blocks a message from user not sending it. But now we want to allow the user to shout it to the world. If we cut the server, how do we tell it to everyone else? So this is where our second tools come into play, which is sampling a communication graph. So very rough idea. There are a lot of subtleties here that I'm not going to get into, but the very rough idea is that the personal committees are going to sample a graph with a small degree and a small diameter. And now instead of shouting to everyone, hey, the server is cheating, they're going to do the opposite. So now every round they're going to say to their neighbors, hey, I'm alive, the user did not cheat. So what happens now if the server does cheat and someone catch him? Well, it means that he's not going to send this message in one round. But then that means that his neighbors are not going to receive a message which tells them that the server is malicious. So they're going to abort. And this propagates through the entire graph because it has polylogarithmic diameter. It means that eventually everyone will abort. Okay, so this solves the second part of the challenge. Right. So to summarize, we introduced the Gulliver MPC model, or GMPC for short, where a single powerful server computes a function over the inputs of many, many weak users. And unlike traditional MPC, here we allow the server to also block messages. And in this model, we constructed the committee election protocol, which allow all parties to agree on a small committee. And to do this, we introduced the tools of personal committees and communication graph, which tackles the block versus abort issue. And I didn't get the chance to talk about it, but using this committee election protocol, we can actually construct a protocol for securely computing any functionality with sufficiently short output. And the protocol is secure, assuming a constant fraction of the users are corrupted, where the constant is strictly less than 1/8, and assuming fully homomorphic encryption exists. However, just like I said, there are many important functionalities where we can actually compute them without assuming FHE and only use signature schemes and commitments. And that's it. Thank you.
Okay, thank you. We have time for questions. 4 minutes for questions. How do you get the mic? Have to run.
Does it work? Yeah, it does. Thanks for the talk. No, I was wondering, like, why is it crucial that you need like FHE? Like, is it related to the size of the messages that?
So the FHE is important for to handle the last challenge of verifying that the server did the computation correctly. We essentially encrypt all the inputs of the users with an FHE, and he will do the computation over the FHE. And then the users are going to verify the computation over the encrypted outputs.
Yeah, but why can't you use, for example, I don't know, garbled circuit approach?
Use what?
A garbled circuit approach. Like, why is it crucial that it's kind of like almost non-interactive? Like, why can't you use another form of two-party computation? I mean, why is it crucial that you need the FHE?
How do you garble the circuits? The users are polylogarithmic, so you need.
Yeah, so I see. So it's related to the
So the circuits could be too big for each one of them to garble.
FHE gets rid of the problem of the.
Yeah.
I see. Okay. Good. Thank you.
Maybe it's related, but I was just curious where this restriction on small outputs comes from. Is it because you polylogarithmic? Is that the issue, or is it?
So again, this relates to how to verify the long statements. After the server does the computation, he will give chunks to each user to verify, essentially. So each user is going to locally do some work on a part of the output, and then they're going to somehow figure it out.
But you said like the output shouldn't be much larger compared to the number of parties, right? So why is there a dependency?
Yeah, it's n times polylog n. So every user will get only polylogarithmic number of bits.
More questions? I was wondering, so without the FHE model, you have very small and shallow circuits. Is that a lower bound, or is it just you couldn't get it?
No, it's not a lower bound. We just noticed that for small and shallow circuits, we can actually do it without FHE. We can let the users do everything on their own.
Okay, thanks. Well, if there is no more questions, let's thank the speaker again. Second talk of the session is titled Fully Secure MPC and ZK, I'm not sure how to pronounce it, FLIOP over rings, new constructions, improvements, and extensions. The authors are Anders Talskov, Daniel Escudero, Ariel Nov. and Daniel is giving a talk. Go ahead, please.
All right, thank you. Hi, everyone. So yes, as mentioned, I'm going to talk today about MPC and rings and zero knowledge proofs. And let's get started on the topic. So first, I would like to quickly state what's the setting that we are working on. So in secure multivariate computations, we know we're going to have multiple parties. I'm labeling P1 to Pn. They wish to compute an arithmetic circuit C on certain private inputs in a way that an adversary corrupting T out of the N parties learns nothing about the honest parties input. So these are I'm just fixing notation as usual, N number of parties, T number of corruptions. And the setting that we are interested in is going to be honest majority. So the adversary is corrupting a minority of the parties. Active security, so the corruption is active or malicious, meaning the corrupt parties can deviate arbitrarily from the protocol specification. We mostly get a statistical security. It's very common nowadays to relax this a little bit for the sake of efficiency, using some PRF here and there, or using the random oracle for Fida-Shamir. I'm going to elaborate more on this, and just clarifying that this is not a theoretical result of pure statistical security. We do use these techniques for efficiency. And this is actually very important. Our talk is about guaranteed output delivery. So I'm going to emphasize on this later, but this is just setting the ground for the context that we study here. What we would like to do in this work is minimizing specifically communication. So I want to get a protocol that is very efficient communication-wise. It's actively secure, and the cost of active security is not that much with respect to passive security. I'm going to be interested in give me the best passively secure protocol. How bad is the corresponding best actively secure protocol? So this is sort of the central question that is going to be surrounding my talk today. Okay, so we have many results studying specifically this question, and I'm citing a few of them here at the very end. I'm going to show this, the references super quickly. So a common design that has taken off during the last few years is taking a passive protocol and somehow compile it into an active one. So this has been a very successful paradigm. And in terms of communication, initially it used to be that we didn't even know very concretely what's the overhead. Like today we know, especially spawning this very important work by Bonnet et al., we know that the cost of active security can actually be made the cost to be the cost of passive plus a sublinear term in the circuit size, multiplied by some factors of n, which I'm ignoring for the purpose of this talk. Passive is usually n times the circuit size, so linear in the circuit size for MPC based on secret sharing and so on. So this means that this term is basically something we can ignore. Asymptotically speaking, this term vanishes as respected to the first term. So in theory, we can say, not in theory, asymptotically, we can say that active security comes for free in the sense that the extra term vanishes as the circuit grows. Okay, so there are many works that have built on top of the previous work to make this even concretely more efficient and address different gaps that the first work left. So that's very important and very cool, and we already know a lot about the communication complexity, but a question remains, and I want to emphasize this one in particular. It's about round complexity. So not many people have explored the question of the round complexity. And specifically for the question of rounds, we know that for passive security, we need a number of rounds that is proportional to the circuit depth. So this is like the main bottleneck, for example, of secret sharing based MPC with respect to, let's say, Garple circuits or other approaches. So we need a linear amount of rounds. For active security with a board, we also need that linear amount of rounds. But for active security with GOD, we need the linear amount of rounds in the depth plus this extra term, which is logarithmic in the size of the circuit. And this is very subtle. It's not like, it's not something that appears in passive security or security with a board. Oh, and by the way, I think this is a good opportunity to introduce GOD, refers to guaranteed output delivery. I mentioned this earlier, is the case when you want to ensure that the parties get the output no matter what. Security with abort is we're finding aborting, we're finding failing if something went wrong. So we are aiming for this stronger notion of guaranteed output delivery. So in this context, if you really want to insist, I want an actively secure protocol that is cheap with respect to passive, then you're going to end up, and you want guaranteed output delivery, you're going to end up paying these extra log C rounds. By the way, I'm writing here, this is even if you assume Fiat Shamir. We're going to be making use of Fiat Shamir for compressing sort of the zero knowledge proof part into a constant round. Even after that compression, you still get an extra logarithmic amount of rounds. So, yep, that's the state of affairs. Actively secure plus GOD, cost passive plus logarithmic in terms of the number of rounds. So there seems to be a gap in efficiency in terms of the number of rounds of passive MPC with respect to active MPC with GOD. So there is this gap. And it's not only a relevant theoretical question, this is minimizing communication is an important goal, but minimizing round count is also a super important goal, if not more, because MPC type of applications are distributed applications are latency sensitive, are quite sensitive to the latency of the network, and the more interaction rounds you have, the more impact this has on the runtimes. So this is bad for high latency settings, for example, if you have a one network, or for instance, if the circuit is very shallow, this extra number of this log C is actually maybe twice, 3 times the size of the number of rounds you will do otherwise if it was passive or active security with abort. So this sets the question. I'm going to just read it out loud. Can we achieve full security for an arbitrary number of parties while incurring only in the following additive overheads with respect to the best semi-honest or passive protocols? Communication overhead that is logarithmic in the circuit size. So I want to keep that property that we already fought so hard to get. That is only an extra small term in communication, but only constant overhead in terms of round complexity, assuming Fiat. Okay. So in that context, our results are as follows. So I would say we get like, we make partial progress towards solving this question. There are like still a few open questions, and I'm going to mention that in a moment. So we present an actively secure protocol with GOD, as I've been mentioning, only constant number of additional rounds with respect to the best passive protocol. It has a small drawback. So first, it works for any secret sharing scheme, which is good. But for the preprocessing, it has a factor of overhead in terms of communication for the offline phase. Offline phase is the phase where it doesn't depend on the inputs party, and it's very common to push complexities to that phase. You still need to run it anyway, so this is not like a full answer, but at least we are able to get an online phase that actually has the same communication asymptotically as the best passive protocol. So we do leave open how to remove this extra factor of in the offline phase. But again, once you address this, the number of rounds will be only a constant additive term extra, with in contrast to other works that is logarithmic in C. If you have any, if you have replicated secret sharing specifically, which works best for a constant number of parties because the share size is exponential, then there you can actually get the same communication as passive security end-to-end. And this is simply because you can do a silent preprocessing where everyone starts from some seeds, and then from some seeds they can expand to secret shares of whatever preprocessing they need. But just emphasizing the bottleneck now is in the preprocessing. So we managed to push things up a little bit. And this is a few tables with some results. Don't want to stay on it for too much, but I just want to emphasize that our work, the 2 results I just mentioned, achieve a number of rounds that is constant, but all the previous works achieve this number of rounds that is logarithmic. And the ones that achieve constant number of rounds are with abort. So we also have some extra results for the T less than in the third regime, and just listening here for completeness, but please see the papers for those details. But I sort of wanted to position our work with respect to all the other related works. Right, and I also want to mention briefly some extra features that I haven't listed. So we try to be very comprehensive. The compiler or our approach works for any ring, even non-commutative. It's actually not super difficult to get it done, and I like thinking of this. How general is this? So a lot of like our techniques turn out to work for even non-commutative rings. I think it's a very interesting observation. And then also interestingly, it builds on this notion of zero knowledge fully linear IOP in a black box way. So if anyone has an improvement on fully linear IOPs, they can be carried over seamlessly. That's the word, yeah, like super easily to our setting. Actually, someone has an improvement in FLIOPs, and that's also us. So we also have some improvements in FLIOPs as a separate thing. I'm not going to get into the details, but FLIOPs are useful over fields, but something I'm very interested in is also rings, specifically the ring C2 to the K. And it's known that if you take the analogous version of a field extension of these rings, you can get most of the things we know on them over fields to work over these rings. They're very useful, and it is known since the first work that basically all these interpolation-based techniques work over these Galois rings. We have an improvement for those techniques specifically that use this technique that has been around for a few years already. The original reference is from 2018, and we leverage RMFEs to improve the FLIOP construction from the original papers. So I'm just listing it for completeness. If you're interested, please check out the paper. I'm not going to talk anymore about like RMFEs or Galois rings or FLIOPs. Right? So for the rest of the talk, I want to focus on how we get these results. And for this, I want to start just by showing how these previous works study the question of MPC sublinear extra cost in communication. Focus is communication for the prior works. So as I mentioned, this CK FLIOP are a very popular receipt for getting sublinear overhead. And the idea is a prover can prove succinctly relations as long as the relation is degree 2 and the values are committed in a way that they can be always opened. So in a way that they can be robustly opened and also homomorphic. So somehow you can take linear combinations of those secrets that are committed. The authors introduced this notion, and then they showed that it can be used to compile passive MPC protocols into active secure ones with sublinear cost. That was a very important result. And for this, they showed 2 different ways of achieving this. And it's called the single prover approach, and the other one is the distributed prover approach. For the single prover approach, each party, this is more like the classical GMW approach. Each party is going to prove to the others that, look, these messages I'm sending to you are correct. And this is sort of the statement. And the CK FLIOP is in charge of proving precisely this statement. These messages I'm sending are correct. And this works as long as the messages sent by the party are degree 2. And most of the time, this is the case because we do this in a gate-by-gate manner. By the way, this also works for smaller degree, bigger than 2. I'm just taking 2 as a prime example. And the values are robustly shared among the parties. Now, subsequent work instantiated this for, so the original work used this for abort and 3 parties, and subsequent work instantiated this for guarantee output delivery, also for 3 parties. Now, the reason why it's important to get to use 3 parties is because in 3 parties, there is only 1 corruption in honest majority. And in that case, either the prover is corrupt and the 2 verifiers are honest, or the prover is honest and one of the 2 verifiers is corrupt. But there is no way that the prover and verifier somehow are simultaneously corrupt. And this means that when the prover is corrupt, the values are trivially robustly shared because the values are held by honest parties. This turned out to be an important property in their construction for getting GOD. I want to emphasize GOD is always harder than abort, mostly because you have to get into these cheating identification issues. You have to try to identify who is the one who sent the incorrect value. For general T bigger than 2, security with abort is possible, but GOD remains a challenge. Security with abort is possible because Shamir is still somewhat robust by on its own. But when you go to the honest majority setting, that's still difficult to get GOD. So the other alternative is to use the distributed prover approach, which is I'm not going to act as a prover. Instead, we're going to compute blindly. And after we compute, we get a lot of secret share values, and we're just going to check, are the secret share values correct? Do they satisfy the correct multiplicative relations? So the original work of Bonnet et al. Used this to compile active security, passive into active security with abort. And with abort, it makes a lot of sense. We can check if the things are correct, and if not, just, well, abort. But the challenge to get GOD is still, it's difficult to detect who is the one who cheated. It's like we found that someone cheated, but still difficult to identify who. So the solution in this recent work, again, towards the end, I showed the citations, is to, okay, we're going to first perform a sublinear check of all these huge amount of multiplications, millions of multiplications, see if they're correct. And if they're not, we're going to start bisecting, making a binary search to find what is the multiplication that failed. And then once we identify the multiplication, we're going to somehow react to this, make an expensive operation that hopefully identifies who is the one that cheated. And this is sort of the extra log C terms come from there. You have to go make this binary search to be able to identify what is the multiplication that failed. So the single prover approach gives you this for n equal to 3, it works, but not for general. And the distributed works, but it costs this extra log C. So what we want to do to address this issue is try to focus on the single prover approach, which is the one that doesn't require this binary search. So how do we achieve this? First, I want to introduce some notation. I'm going to use Shamir secret sharing for this example. Remember, it works for any linear secret sharing scheme. The square ones are going to be Shamir, and the angled ones are going to be additive secret sharing. And let's start from the DNO7 protocol, listing it here for completeness purposes. So if you want to multiply two values, you multiply locally and add a random value to it. That gives you additive shares of this addition. You reconstruct it to a party, P1. This party learns that that's addition, sends the addition to all the parties, and then the parties subtract, this is typo here, they subtract the square sharings to get the square sharings of XY, or like Shamir sharing of XY. And there is this fact that basically actively security boils down to all these multiplications, proving that these multiplications were done correctly. That's all you need to get active security. There's minor things on consistency and so on. That's all that you need. So let's introduce a little bit more notation. So I'm going to denote the input, left input, right input, and output inputs of all the multiplication by X, Y, Z. And the goal is to check that the parties send the right messages to each other.
3 minutes.
3? Okay, thank you. So I'm going to use superscripts for the party shares. So let xi, yi, and ri be the shares of x, y, and r respectively. Let message 1i be the message that pi sent to p1, which should be equal to this. We're going to hopefully prove that that's the case. And let message 2 be the message that p1 sent to the parties, which should be equal to the sum of the messages that were in common to p1. So the goal is to check that indeed the parties did this correctly. And this is sort of the equations that we need to prove. So jumping ahead a little bit, the first idea, as usual in a lot of MPC protocols, is first we're going to compress via random linear combinations. So you just take a random linear combination of all these equations we want to check. And now we only need to check one single equation, which is this one. We just need to show that this random linear combination here, which is the random linear combination of the shares, random linear combination of the shares of R, and random linear combination of the message, they subtract to 0 as explained here. And this one is just the messages sent by P1. So then we are going to let the parties commit to their to these compressed shares by just broadcasting it to each other. It is fine to broadcast this because it's a compressed version of all the wires. So it's constant cost. So the parties are going to broadcast all these compressed messages. We're going to handle inconsistencies. I'm not like, basically this is usually in GOD. If someone sends something and the other person disagrees, they're gonna end into a disagreement, and then somehow you're gonna resolve a dispute. So I'm ignoring all these GOD related terms here. And once you have this compressed transcript, we have to check again this equation. How do I jump from this? Sorry?
30 seconds. 30 seconds.
All right. So this is the equation I want to check. So the only thing I really want to sort of transmit, the message I want to transmit is, we have shares of this, we have shares of this, we have shares of this, and we're missing shares of the R. So I'm not gonna show the slide, but basically the quadratic term in the preprocessing comes from this R. This R is a value that we don't have robustly shared. So basically, we propose different ways of robustly sharing this R. And all the ways we came up with really incurred in a term that is n squared, like basically having robust shares of the parts. So this is where the bottleneck is. Didn't get time to get to it. We'll scroll towards the end, just showing the references for completeness in the video, but of course the slides will be made available. And yep, this is the conclusions in the screen, and then thank you.
Thank you. Just about finished. If there's super quick question, then maybe we can take it. If it's not super quick, then save it for later.
Yeah.
And let's move on to the. Oh yeah, let's thank the speaker again for finishing just about on time. And the next speaker is setting up. The next third paper in this session is computation efficient structure aware PSI from incremental function secret sharing by Gayatri Garimella, Benjamin Goff, Peihan Miao, and Gayatri is giving a talk. Go ahead.
Thank you for the introduction. So today I'll be talking about a new result in structure-aware PSI. So private set intersection, or PSI, is a special case of two-party secure computation. So here you have Alice, who has a private collection of elements, and you have Bob, who also has his private collection of elements. And Alice, who's the designate receiver, wants to identify the common elements between her input and Bob's input. PSI has a long line of work, and many different approaches have been used to solve this problem. Many different settings have also been considered, which are often motivated by real-world applications. And my focus for today's talk is this variant of PSI that we call structure-aware PSI. It was introduced in 2022 in a joint work with Mike Rosalick and Jaspal Singh. And here, Alice's input has some publicly known structure. For example, Alice's input could come from the set family of a one-sided interval, or it could be a ball, or a union of balls as shown here within some well-defined metric space. And on the other side, you have Bob, who has an unstructured collection of points within the same metric space. And the goal is to enable Alice to identify all the points that lie within her chosen structure. And one of the motivations for looking at this problem is this cool application called fuzzy matching. So imagine that you're trying to build a privacy-preserving ride-hailing service. So you have a set of ride-hailers who care about their privacy and don't want to reveal their GPS coordinates in the clear to the service. On the other side, you have a set of available rides in the area. So one way to model this problem is to define a delta radius ball centered around each of these ride-hailers. And if you could do a matching between these two data sets, then you would realize this very cool application. So let's look at how you would attempt to achieve a protocol for structure-aware PSI. A naive solution is to just ignore the fact that Alice's input has any structure. You simply enumerate all the points that lie within her chosen structure, and then you run any existing plain PSI between Alice's input and Bob's input. But this is undesirable because all known PSI protocols have communication and/or the computation to scale with the cardinality of the inputs of Alice and Bob. And in this case, Alice's input, which is a structured set, may have prohibitively large cardinality. So our focus is to instead have the communication and computation scale with a much more succinct description size of Alice's input instead of the cardinality of her input. And we want to leverage the fact that Alice's input comes from this publicly known structure. And the starting point of our framework is this semi-honest framework for structure-aware PSI. And what this achieves is that the communication cost of this protocol scales with the succinct description of Alice's input. And another advantage of this work is that it essentially builds from lightweight symmetric key-based operations and OT extension. But a limitation of this framework is that the computation still scales with Alice's cardinality, which could turn out to be a bottleneck. And this is our main contribution in this work. We propose a new framework for semi-honest structure-aware PSI, where both the communication and computation scale with the succinct description size. And we continue to have this advantage that we essentially build from lightweight operations. So for the rest of this talk, I'll first revisit this previous framework, and I'll explain the primitives that we used to build it. And then I'll show how they realize this framework. And then I'll motivate this new primitive called incremental Boolean FSS and show how we get this new framework, which has these desirable properties. So first, we'll start with looking at Boolean function secret sharing. So this idea of function secret sharing was introduced by Boyle, Gilboa, and Ishai in 2015. And we kind of adapt their definition for the set membership functions. So if you have a structured input A that comes from a set family S, then you can essentially secret share any input from this set family such that you end up with these two shares, this blue share and pink share. And each of these shares are pseudo-random, so they completely hide the actual input that you're secret sharing. And it has this additional property that you can evaluate on these FSS shares for any point in your domain. And if that point lies within your chosen structure, then your evaluation on the blue share and the pink share will match. So if you XOR them, the result is 0. And if you evaluate this point on any point outside your chosen input, then these evaluations don't match. So you might be able to start to see that this can be a useful tool for testing set membership. And the second primitive we need is oblivious transfer. So this is a two-party primitive where Alice has two messages, and Bob is allowed to learn exactly one of these two messages. And the guarantee is that Alice is completely oblivious of which of the two messages Bob learned. And OT can be instantiated efficiently thanks to OT extension. So let's see how this prior framework utilized these primitives. So Alice has this input that comes from a structured family, and suppose you have this FSS scheme for that chosen set family, then Alice secret shares her input 128 times, security parameter number of times. And Bob gets to pick whether he wants to learn the blue share or the pink share for each of these instances of sharings. And then they run an oblivious transfer for every instance so that Bob learns exactly one share for every instance of sharing, either the blue or the pink. After this, Bob can locally define this function f, where to evaluate this function f on any point, he simply evaluates each of these FSS shares on that point, concatenates the result, and computes a hash on it. So the crucial feature to observe about this function is that it entirely contains all the information about Bob's choice bits. And this is something that Bob knows, so he can compute this function for any input of his choice. And in particular, he chooses to compute this function for every single input within his chosen set and sends it to Alice. Now, from Alice's perspective, for any point within her chosen input, she has the ability to compute this function. This comes from the property of the FSS because it doesn't matter whether you evaluate on the pink share or the blue share, your evaluations will match. So she doesn't really have to guess what Bob's choices were. So for every point within the structure, she can compute this function f. And crucially, for every point outside the structure, she can't compute this function f. And it looks completely random to her. So that's the protocol. Alice has to compute this function for every single point within her chosen structure. So she computes this function, enumerates it, and locally compares the value she computed with Bob's function evaluations. And every time there's a matching value, she can figure out that this point lies within her structure. But this is the undesirable property that we're addressing in this work. Notice that Alice has to enumerate and compute this function for every point within her set. And we want to address this with a new approach. And on a high level, this is the idea. Alice sends these function evaluations, but along with that, now he'll send some specially crafted hints. And these hints should enable Alice to efficiently identify and search for values within her input instead of having to enumerate everything. And for this, we'll use the primitives of incremental Boolean FSS. I'll talk about what properties we want from it and how we get this framework. But for this, I'm going to restrict myself to a very simple instance of PSI as a working example. So imagine that Alice's input is this structure, which is a one-sided interval. So it's from 0 to alpha, where alpha is hidden from Bob. And Bob's input is a single point. And what Alice is supposed to learn is if this point belongs to her interval, she wants to find out the identity of this point. And if it's outside the interval, she just learns that fact and nothing else. And recall that previously, Alice, when she had such a structure, she would have to secret share it. And she would have to enumerate this, she would have to compute this function for every single point in the domain within her set. But let's revisit the idea of how you would actually figure out if a given point B lies within your interval. Like, how would you actually identify if a point lies within your interval? Well, you could represent your domain as leaves of this binary tree, and alpha could define this critical path. Now, if you want to figure out whether your point B lies within alpha, then you just do a bitwise comparison. And if you deviate to the left of this critical path, you immediately know that your point is in the interval. And if you deviate on the left, then you know that it's outside this interval. And this is the exact idea that we want to leverage and mimic in our FSS scheme. So we identify all these, so the minute you deviate from this critical path, we identify all these nodes as our critical prefixes. And crucially observe that these set of critical prefixes jointly span the entirety of Alice's input. So now we would like an FSS that looks like this, where you not only secret share points in the domain, but you also secret share this entire tree. So you also consider all the prefixes of this tree. And you have this incremental evaluation where you can evaluate not just on the leaves, but all the intermediate nodes. And this idea of incremental evaluation is not totally new. Our inspiration comes from this work by Bonnet et al. From 21, where they use this idea of incremental evaluation for a very specific class of distributed point functions in the context of private heavy hitters. And more recently, we're seeing more works that use incremental DPF, but we need something a little bit more general. So we, in our work, we formalize this notion of incremental FSS, and then we provide definitions and constructions in the paper, but crucially observe that once you secret share this tree, every time you deviate from the critical path and all the nodes that fall within that subtree have matching values when you evaluate on these different shares. And along the critical path, and when you deviate to the right of it, the values don't match. So let's see how you can use this for FSS. So imagine that you have just a single instance of OT and Bob learns the blue share. So Bob has a single input B. And this input, and you can identify all the prefixes of his input. So Bob now kind of has the ability to use this share to not just evaluate on B, but he can also evaluate on every single prefix of his input. And then these will serve as our hints. And Bob sends these across to Alice. Now, from Alice's perspective, say she picked the pink share. She knows her structured input, so she can identify what the critical prefixes are. And she can use this pink share to compute the evaluation on each of these critical prefixes. And then she can locally compare with the hints that Bob sent. And the invariant is that if the point B lies within her interval, then Alice will certainly find a matching value corresponding to the critical prefix. And in fact, once you find this critical prefix, the rest of the path to this point B is also computable by Alice. She just has to reuse these hints in a special way and do a binary search, but I won't have time to talk about it. And the crucial thing is that in case B, because Alice is evaluating on this pink share, none of the evaluations will match, and she just learns that Bob's point is outside her interval. Now, Alice kind of picks this pink share with probability half. And if she ended up picking the blue share, then she would learn more than she's supposed to. So in the full protocol, we do 128 instances of OT. And what Bob now does is, in the usual way, he defines this local function f, where he evaluates his point on every single FSS share, concatenates the result, and computes the hash on it. And he computes this for every single prefix, and these serve as the hints. So this is how the full protocol works. And Alice, again, can compute this function for all her critical prefixes, find the matching value, and ends up with one of these two cases. And I'll defer to the paper for you to see how you can figure out the exact, how you can identify what the exact point B is. Yeah, and a little bit about the cost comparison. So if you compare with this previous framework, you notice that Alice's computation reduces. Here, delta is the size of the interval. So now Alice doesn't have to compute on the entire interval. So there's a reduction in her computation. And there's also a slight increase in Bob's communication. But you really start to see savings when you start looking at more complicated structures. I've shown a very simple example here. And yeah, in the paper, we also explore more complicated structures. So prior work studied d-dimensional intervals, and they showed a nice trick to compose different FSS using this AND composition. And we show that this is also compatible in this new FSS variant. So these tricks can be lifted to our setting as well. And we also consider more complex structures like this union of balls. And we show new observations that achieve, so we qualitatively improve prior work because now we can also handle potentially overlapping structures. And all prior work was strictly restricted to the fact that the structures were disjoint. And we also improved like the asymptotics of these. So I'll defer to the paper for that. And then we also look at extending functionality. So you notice from our framework that only Alice learns the output, but there might be potential applications where you might want Bob, the party with the unstructured input, to learn the result, the intersection. So we show how this can be achieved. We also explore extending the functionality beyond just the intersection. So these are well-studied functionalities where called PSI cardinality or PSI sum, where you want to reveal the cardinality of the intersection instead of the actual values that lie in the intersection. And we show how you can achieve these. Yeah, and finally, I'll talk a little bit about future directions and what we're excited about. So it'll be really interesting to find new real-world applications that motivate different types of structures that are interesting, and then to build FSS for these kind of structures that are compatible and useful in the context of PSI. It'll also be interesting to extend our techniques to other distance metrics while continuing to have the advantage that we build from lightweight operations. And we'd also like to see if we can extend our ideas to the malicious setting. There was a framework for malicious proposed last year, so we want to see if they're compatible. And we also want to revisit the malicious framework and see if it can be improved by itself. And with that, I'll conclude.
Thank you. Let's see if we have questions. No question. So for what I understood, you have multidimensional intervals, basically, that's it, or intersection of multidimensional intervals. So that's useful for some fuzzy authentication, maybe like fingerprint facial eventually. Did you try to translate it into the actual biometrics or?
No, we'll have to see how to do that. Like, yeah, I think biometrics come with like long features, and then you have, what is the notion of closeness is something that has to be formalized.
For sure. Yeah. There's a gap there. Okay. There is no more questions. Let's thank the speaker again. Okay, and the last talk of the session is on compressing unit vector correlations via sparse pseudorandom generators by Amit Agarwal, Eled Boyle, Yves Gilboa, Yuval Ishai, Mahima Kelkar, and Yiping Ma. And Amit is giving a talk. Go ahead.
Can you hear me? Can you hear me? Well, can you hear me now? Hello. Hello. Can you hear me? Okay. Hi everyone. Today I'll be presenting this work on compressing unit vector correlations via sparse pseudorandom generators. And this is joint work with my co-authors, Elliot Boyle, Yves Gilboa, Yuval Ishai, Mahima Kelkar, and Yiping Ma. So let me first start with the motivation. So a popular paradigm in secure computation is a so-called offline-online secure computation model, also known as the pre-processing model. Here, this Alice and Bob, they want to compute some function f securely on their inputs x and y. So to do this, we divide the protocol into two parts, an offline part where the inputs are unknown, and parties use random inputs to interact to form so-called correlated randomness. And then in the online phase, inputs of the parties become known, and they use the produced correlated randomness to securely compute the function on their private inputs. And some examples of this correlated randomness includes Beaver triples, random OT correlations, and so on. And the idea is that we want to do this to achieve online efficiency in terms of communication and rounds, and sometimes also computation. So let me now define correlations a bit more formally. So it's very simple. We have some public distribution D, and we sample an element R from such a distribution, and then additively secret share R among the parties, which is illustrated in this following figure. And the sharing of the parties across all parties will be the correlation with respect to the distribution D. So for example, if you instantiate this distribution with uniform distribution over all triples A, B, and C, such that C is A times B, then the induced correlation is what we call Beaver triple correlation. So a central question in this offline-online MPC paradigm is how do we go about efficiently generating and compactly storing many independent instances of such correlated randomness? So a nice approach to this question is via designing so-called objects called PCGs, short for pseudo-random correlation generators. So think of PCG as a distributed form of standard PRG, where we have some gen procedure which will distribute short correlated seeds across two or more parties. And then the parties can expand this seed into long pseudo-random correlated strings. And the benefit here is that the expansion procedure only takes communication which is sublinear in the length of the output correlated randomness. So let's say the output length is n. Then the correctness says that the joint distribution of the outputs of the parties is indistinguishable from an additive sharing of a sample from n copies of the distribution D over which the correlation is defined. Security says that if one of the parties, let's say Alice, is corrupt, then the joint distribution of the seed of the corrupt party with the output of the honest party is indistinguishable from the seed of the corrupt party jointly with the reverse sampled output of the honest party. So there are many existing works which explore PCG constructions, but they are limited to simple correlations such as multiplication triples, random oblivious transfer correlations, and oblivious linear evaluation correlations. While using generic techniques, you can extend them to richer correlations, but this is practically inefficient. So in this work, we explore a practical PCG for a useful correlation called unit vector correlation. Let's see what this is. So earlier in my slides, I had this diagram of what any generic additive correlation is and it's defined with respect to some public distribution D. And now if we instantiate this distribution D with a uniform distribution over all unit vectors of a fixed length, then the induced distribution is called a unit vector correlation. Induced correlation is called the unit vector correlation. And I'll term that as UV correlation for short. It's nothing, basically, parties are holding additive shares of a random unit vector where the non-zero location of the unit vector is secret. And some applications of this UV correlations include secure lookup table evaluations, online optimal private information retrieval. And this can also provide a middle ground in terms of generic MPC, FHE and OT-based generic MPC. So for example, FHE lets you achieve optimal communication, but is computationally heavy. On the other hand, OT has good computation, but the communication scales with the circuit size. UV correlations allow you to have slightly sublinear communication at moderate computational cost, which might often strike the right balance in practice. So now the question is, can we design a PCG for such UV correlations? So the starting point is this well-known PRG plus HSS framework for designing PCGs, which uses two objects, PRG and HSS. Let's see what they are. So a PRG, as you all know, takes a uniform seed and expands it into a long pseudorandom string R. HSS can be thought of as a distributed form of FHE. So you have some input X, and the HSS share procedure will let you split this input across two or more parties. And then the parties can locally evaluate some function f homomorphically on their shares to derive output shares, which will sum up to f of x. Now, using these two objects, we can get a PCG in a straightforward way. The idea is simple. So you take the PRG seed S and use the HSS share procedure to split the seed across the two or more parties. And this will be our PCG gen procedure. Now, the parties can take their splits of the seed and do an HSS eval procedure on a function f for a very specific f. So this function f would be the expansion procedure of the PRG composed with another function, another deterministic function, which maps a uniform distribution into the required distribution D of interest. And if they do this HSS eval procedure, they would end up with an additive sharing of the distribution D over which the correlation is defined. So we can, and you can think of this blue triangle as the PCG expand procedure now. So one can directly use this template to also construct UV correlations. But the downside is that evaluating this function f, which I recall is a composition of the PRG expansion procedure and a deterministic mapping from uniform to non-uniform sparse distribution, is quite costly inside HSS. And the reason is that this mapping from uniform to the required distribution D, which in our case is the UV unit vector distribution, is a high degree computation. So our solution to this problem is to design a low degree equivalent of this function. And this is what we will term as a sparse pseudorandom generator in our work. So now let's define that object a bit more formally. So we all know standard PRG takes a uniform seed and outputs uniform pseudorandom bit string. A sparse PRG, on the other hand, outputs a sparse pseudorandom bit string. And in our case, we will explore a regular sparse distribution, which means that every consecutive block of some fixed number of bits will have exactly a single non-zero entry. So for example, in this diagram on the right, you can see every block of 4 entries has a single non-zero entry, where the location of that non-zero entry would be pseudorandom. So this is a sparse distribution. And we will also allow arbitrary seed distributions. So in a PRG, we usually deal with uniform seed distributions. In our case, we will allow arbitrary seed distribution, and this would be very necessary to achieve our goals later. So at a very high level, what we'll do is we'll design this object And then we will run this object, the sparse PRG object inside HSS. To have an efficient PCG, we will want to have a low degree sparse PRG, where the degree is, so if you interpret each output bit of the sparse PRG as a multivariate polynomial over the input bits, then we want to control the degree of that multivariate polynomial. So how should we go about constructing such sparse PRGs? So one idea is to just map the uniform output bits of any standard PRG to a non-uniform sparse distribution. But then the caveat in this approach is that, as we discussed, this increases the degree of the overall PRG. Another possible approach is to supply a standard PRG with non-uniform seed bits instead of uniform seed bits, but this runs into some security issues. So our approach to this problem is to leverage non-binary local PRGs. So let's see what they are. So let's see what non-binary PRGs is as a first case. So in non-binary PRGs, the inputs and outputs are no longer bits, but they are symbols from some alphabet set. Let's say the alphabet set is 1, 2, 3, 4. Now the seed will have random symbols from this alphabet set, and the PRG will expand it into a pseudo-random set of symbols from the same alphabet set. Now, one starting observation is that if we just encode the output symbols of this PRG, non-binary PRG, in a sparse unit vector format like this, then we directly get correctness and security for free. And let's see what this encoding is. Some people call this as also one-hot encoding. So if you look at this symbol 2 on the right, it got encoded into 0, 1, 1, 0, 1, 0, 0. Which means that there's a non-zero location is at second location. If you look at symbol 4, it gets encoded into 0, 0, 0, 1, meaning that the non-zero location is at entry 4. So this is the unit vector or the one-hot encoding, which I'm talking about. So we get this sparse pseudo-random, sparse PRG. And as I said, the correctness and security directly holds from the security of the underlying non-binary PRG. But it's not clear what the degree of such a PRG is. In fact, the degree can be as high as the seed length. And we don't want that. We want a low degree sparse PRG because later this will control the complexity of the PCG that we construct. So now our goal is to construct low degree sparse PRG. And for that, we will leverage another property from the underlying non-binary PRG, which is called small locality. So now what we'll say is that the non-binary PRG has small locality. In this diagram, it's 2, which means that every output symbol of the non-binary PRG depends on small number of input symbols, in this case, 2. So now the idea is that if given such a non-binary local PRG, you also encode the input symbols of the seed in a sparse unit vector format like this, then you get a sparse PRG with low degree. In fact, the degree of the object on the right would be exactly identical to the locality of the object on the left. Okay. So going into a bit more detail, let's see how that works. So on the left side, I have a non-binary local PRG. And on the right side, I have the sparse low degree PRG, which we obtain by just encoding the output and input symbols in the sparse unit vector format. So let's say the output symbol Z is obtained by applying some function f on the input symbols x and y. So what you can do is you can rewrite f of x comma y as this expression on the right, which basically is saying that if input x is 1 and y is 1, you output f of 1 comma 1. Or if input x is 1, y is 2, you output f1 comma 2, and so on. So note that this expression has like equal. Oh, sorry. How do I go back? So this expression has equality checks, which is a high degree computation. But in the sparse world on the right, we already have a sparse encoding of the input symbols. And so we can rewrite this expression in the following form. x1 times y1 times f of 1 comma 1 plus x1 times y2 times f1 comma 2. Basically, the equality checks become a low degree computation in the sparse world where you already have a sparse unit vector encoding of the seed symbols. And this is what enables low degrees sparse PRG. So in summary, we show that if you have a local PRG with locality D over some alphabet sigma, then you can get a sparse PRG with low degree, where the degree is equal to the locality of the PRG that you start with, and the sparsity size is equal to the alphabet size. And then you can use any homomorphic secret sharing scheme for computing degree D polynomials to compile it into a PCG for UV correlations. There are different options for instantiating such an HSS scheme, such as in the honest majority setting. You can use information theoretic HSS based on some secret sharing or replicated secret sharing. In the dishonest majority setting with 2 parties and 1 corruption, you can use HSS based on DCR, quadratic reciprocity, group-based assumptions, and also lattice-based assumption. So in our work, we show that some further optimizations. For example, we can compress the PCG seed size further using so-called multiplicative DPF. It's a form of distributed point function where the output shares form a CNF or replicated secret sharing. And hence, you can multiply the shares locally up to a certain limit. And our construction has an improvement over the prior 3-party 1-secure multiplicative DPF construction from Boone et al., both in terms of number of parties that we can support and also the seed size, improvement in seed size. And this helps us in improving the resulting PCG seed size from being proportional to linear in the sparsity parameter to being proportional to just log in the sparsity parameter. And this has other applications, such as securely searching a document that contains D keywords using just D+1 non-collating servers, whereas previous approaches required exponential ND non-collating servers. And our approach can also support HSS with just multiplicative reconstruction. So note that in the literature, many HSS schemes with additive reconstruction require this problem of solving distributed D-log, which forms a computational bottleneck. And we show that a variant of UV correlations where the non-zero entry is a random weight entry instead of just being 1 can be generated using HSS with just multiplicative reconstruction. And this enables us to use existing HSS schemes without invoking the distributed D-log procedure. And we also show that this variant of weight 1 UV correlation can be converted into the standard UV correlation with low communication. In our paper, we also explore different candidates for non-binary local PRG. So as a naive observation, we observed that any D-local binary PRG can be used to get a D-local non-binary PRG simply by running many copies of it. And for D-local binary PRG, you can instantiate it, for example, using 5 local Goldreich style PRG with TSA predicate. We also explore direct constructions of 3 local non-binary PRG. And we term this candidate as sparse learning with rounding candidate. And this is motivated by hardware optimizations of the resulting PCG. And this candidate is inspired from the sparse learning parity with noise assumption based candidate and existing learning with rounding candidate in the literature. Okay, let me just give a brief highlight of how this candidate looks like. So let's say you have some output symbol, Y, which—
You have 1 minute.
Okay, yeah, sure. So what we do is we take random public permutations of the input symbols at, let's say, 3 different locations, X1, X2, X3. We add them up and then we round. It's a very simple candidate. And this rounding parameter, can be a parameter of the PRG. In this case, it's 2. There's also an existing candidate from Barak et al. Based on non-abelian groups. We also provide a candidate for 2 local non-binary PRG in the paper. So we note that non-binary local PRGs have been used before for constructing I/O. But in such I/O use cases, the requirement is of a large input alphabet, whereas we require a large output alphabet. And some barriers on the parameters of two local non-binary PRG were proposed in prior works, which rules out I/O constructions, but not PCG applications. We also show that we can extend to authenticated unit vector correlations, which might be useful for malicious secure MPC. Here are some highlights of cost estimates. In the honest majority setting, we can produce length 16 unit vectors with a throughput of 10^5 unit vectors per second and a seed size of 300 kilobytes and compression ratio of 79. Compression ratio is defined as what is the with respect to what is the best known baseline for compressing a given number of output UV vectors with the best known practical construction in the literature. In the two-party one corruption case, we can produce length 8 unit vectors with a throughput of 1 UV per second. So the costs here are not that good compared to the honest majority case.
I hope you finished now.
Yeah, so
Okay,
thanks.
Let's thank the speaker. Okay, so since we don't have any more time, we can catch the speaker after the talk during the coffee hour. Let's thank the speaker and all the speakers of the session.